Hello everyone, I'm Prakya Jain, Assistant Professor, Department of Mechanical Engineering, HIT Mangalore. Today I'm going to discuss about Module 4 of Fluid Mechanics. This is a continued portion of dimensional analysis. The syllabus include Buckingham Pi theorem and problems. So before going to Buckingham Pi theorem, let us just discuss drawbacks or limitations of Rayleigh method. The Rayleigh method of dimensional analysis becomes more laborious if the variables are more than number of fundamental dimensions, that is m, l and t. This difficulty is overcome by using Buckingham Pi theorem. So this Rayleigh method can be applied to a problem if the number of independent variable is more than 3 or 4. So that is more than number of fundamental dimensions. So number of fundamental dimension is equal to 3, that is m, l and t. So by if we have a number of independent variable or number of variable as 3, then we can get 3 expressions by equating the powers of m, l and t. So we can easily solve that type of equations by using simultaneous equation method. Now what if the number of independent variable crosses more than 3, that is 3 or 4 or more than 5? So that type of problems can be solved by expressing 3 variables, say a, b, c, in terms of remaining 2 if the number of variable is 5. So a, b, c can be expressed in terms of other 2 variables, say d and e. So we should go for elimination method. So in doing that elimination method, we have to select repeating variable or some parameters which is important for the problem. So that is very difficult to judge. So that's why Rayleigh method has complexity in solving the number of, if the number of variables is more than 3. So we should go for some alternative. That alternative here is Buckingham Pi theorem. So what is Buckingham Pi theorem states? So it states that if there are n variables, that includes independent and dependent variables in a physical phenomenon, and if these variables contain m fundamental dimensions, that is m, l and t, then the variables are arranged into n minus m dimensionless terms. Each term is called pi term. So if there are n variables, that includes both independent as well as dependent variable, and if we have m dimensions, that is fundamental dimensions from the variables, then so that variables can be grouped into n minus m dimensionless terms. So that dimensionless term is called pi term. So we can categorize or we can classify the variables into n minus m terms, where n is number of variable and m is number of fundamental dimension. So that is a statement of Buckingham Pi theorem. So now let's go for the procedure of steps involved in solving Buckingham Pi theorem. For solving the dimensional analysis problem, the following step are to be followed. So first step, let x1, x2, x3 up to xn are the variables involved in a physical phenomenon. Let x1 be the dependent variable and x2, x3 up to xn are the independent variables on which x1 depends. Then x1 is a function of x2, x3 up to xn, and mathematically it is expressed as x1 equal to f of x2, x3 up to xn. So if we have variables, say x1, x2, x3 up to xn, so that includes both independent as well as dependent variable. So for time's sake, here they are taking x1 as dependent variable. So it is dependent on remaining variables, say x2, x3, xn up to xn. So we can express such type of expressions as a like for independent variable can be expressed as a function of independent variable, that is x1 equal to f of x1, x2, x3 up to xn, where x1 is dependent variable, x2, x3 up to xn, those are independent variables. So that equation 1 can also be written as f1 of x1, x2, x3 up to xn, that is equal to 0. So equation 1 is x1 equal to f of x2, x3 up to xn. So that can be also written or simplified as f1 of x1, x2, x3 up to xn equal to 0. Take it as expression 2. Next, step 2. Equation 2 is dimensionally homogeneous equation. it contains n variables. If there are m fundamental dimensions, then according to Buckingham Pi theorem, equation 2 can be written in terms of dimensionless groups or pi terms, in which number of pi terms is equal to n minus m. Hence equation 2 becomes as f of pi 1 comma pi 2 up to pi n minus m equal to 0. So equation 2 is dimensionally homogeneous equation. Hope you know what is dimensionally homogeneous equation, and it contains n variables. That includes both dependent as well as independent variable. And if it has m fundamental dimensions, then according to Buckingham's Pi theorem, it can be grouped into n minus m dimensionless term. So dimensionless term is called as pi term. So we can get n minus m pi term from the number of variable as well as number of fundamental dimensions. So equation 2, that is f1 of x1 comma x2 up to xn equal to 0 can be expressed now or rewritten as f of pi 1 comma pi 2 up to pi n minus m equal to 0. So take it as expression 3. Next, step 3. Each of pi terms is a dimensionless and is independent of the system. Division or multiplication by a constant does not change character of the pi term. Each pi term contains m plus 1 variables, where m is the number of fundamental dimensions and is also called the repeating variable. So as we all know, a pi term is a dimensionless. So it is independent of the system. That means whatever the system you are going to follow, like it may be CGS or MKS system, it has no unit. So because it's a dimensionless. So a division or multiplication by a constant does not change the character of the pi term. So we can multiply or divide by any constant, that is not going to change value of the pi term. So each pi term contains m plus 1 variable. What is m there? M is number of fundamental dimensions. So each pi term contains m plus 1 variables. So it should have more, like if number of fundamental dimension is 3, then pi term should have 4 variable or 4 terms. So that m is called as repeating variable. So number of repeating variable is equal to number of fundamental dimensions. So let in the above case x2 comma x3 and x4 are repeating variable if the fundamental dimension m equal to 3. So if we have fundamental dimensions as m, l and t, so number of fundamental dimension m equal to 3. So each pi term should contain 3 plus 1 variable, that is 4. So we have to select now repeating variable. So here they have taken x2 comma x3 and x4 as repeating variable. Then each pi term is written as pi 1 equal to x to the power a1 comma x3 to the power b1 into x4 to the power c1 into x1. So where a1, a2, a1, b1, c1 are constants or powers, and x2, x3, x4 are already taken as repeating variable. From the Buckingham Pi theorem, we have to express pi term into we have to express pi term in pi term should have m plus 1 variable. So m is equal to fundamental dimension. Now we already taken repeating variable as 3, like x2, x3 and x4. So now one more term we have to include into pi term. So that is here they are taken as x1. So pi 1 equal to x to the power a1 into x3 to the power b1 into x4 to the power c1 into x1. Next, similarly pi 2. So other than x1, x2 and x3, x4, we have the remaining terms like x5, x6 up to xn. So in place of pi 2 equal to x to the power a2 into x3 to the power b2 into x4 to the power c2 into x5, because we already expressed x1, x2, x3, x4 we already used. So but in pi 2 x2, x3, x4 are repeating variable. So other than x2, x3, x4 and x1, remaining variable is x5. So just multiply to pi 2. Next, similarly we can follow like that till pi n minus m, that is equal to x to the power an minus 1 m, x3 to the power bn minus m, x4 to the power n minus m into xn. So take it as expression 4. Next, step 4. Each equation is solved by principle of dimensional homogeneity and values of A1, B1, C1, etc. are obtained. These values are substituted in equation 4 and values of pi 1, pi 2 up to pi n minus m are obtained. So expressions for pi 1, pi 2, pi 3 that can be solved by using a concept of dimensional homogeneity. So that is left hand side dimension should be equal to right hand side, so that we can get values of a1, b1, c1, a2, b2, c2 and so on. So we can back substitute values of a1, b1, c1 and a2, b2, c2 and so on in expression 4, that is for expressions for pi 1, pi 2 up to pi n minus m. So we can get values of pi 1, pi 2, pi 3 up to pi n minus m. Next, last step, step 5. These values of pi's are substituted in equation 3. The final expression for phenomenon is obtained by expressing any one of the pi terms as a function of this. So after getting pi 1, pi 2, pi 3 value, we have to substitute in equation 3, that is function of pi 1 comma pi 2 up to pi n minus m equal to 0. We have to substitute values of pi 1, pi 2, pi 3 in equation 3, so that, and we have to express one pi term as a function of other pi term. So here for time's sake they have taken pi 1 first pi term as a function of pi 2, pi 3 up to pi n minus 1, or you can take second pi term as a function of pi 1, pi 3 up to pi n minus m. So that is equation 5. So these are the steps involved in Buckingham Pi theorem. Next, method of selecting repeating variable. So we cannot select repeating variable like by judgment. So we have to follow some procedure for selecting the repeating variable. So let us just go for that. So the number of repeating variables are equal to number of fundamental dimensions of the problem. So as I already told, number of repeating variables should be equal to number of fundamental dimension. If number of fundamental dimension is equal to 3, that is m equal to 3, then number of repeating variable also should be equal to 3. The choice of repeating variable is governed by the following consideration. First one, as far as possible, the dependent variable should not be selected as repeating variable. So you cannot select dependent variable as repeating variable. Second one, the repeating variable should be chosen in such a way that one variable contains geometric property, other variable contains flow property, and third variable contains fluid property. If we have three repeating variable, then one first variable should correspond to geometric property, second variable correspond to flow property, and third variable corresponds to fluid property. This is a procedure: first geometric, then flow, then fluid property. So the first repeating variables with geometric property are, there are some parameters that can be considered as geometric property. Let us just go through that. First one is length L, diameter D, height h, width w, etc. We can select any one of the following as first geometric property or geometric variable. So depending on the condition. The second repeating variables with flow property are, so flow property that is related to motion. So for geometric property that is related to geometric shape or size. So length, width that comes into picture. Whereas second repeating variable correspond to flow property that is related to the motion. So what are the parameters governing motion? Say velocity, acceleration, force, power and speed. So that has to be taken as repeating variable with flow property. So we can select any one of the following: velocity, acceleration, force, power and speed depending on the condition. Then third repeating variables with fluid property. So this is related to property of the fluid. What are the properties of fluid? We already discussed in module 1. Density, specific weight, viscosity, surface tension, capillarity and all. So we can select the property based on following, like any one of the following: density, specific weight that is represented by small letter w, viscosity mu, surface tension sigma. So three variable repeating variable with one corresponds, first corresponds to geometric, second flow, third fluid property. That has to be taken care. So third point, the repeating variable selected should not form a dimensionless group. So whatever the repeating variables you are going to take, like it should not from dimensionless form, that is power m to the power 0, l to the power 0, t to the power 0 upon combination or clubbing together. So we should not get a dimensionless or unitless term. Next, fourth one, the repeating variables together must have same number of fundamental dimensions. So repeating variables should have same number of fundamental dimensions, that is m, l and t. So repeating variables should have at least in one parameter m, and in second one l, and a third one it should have t. So that's the meaning of this sentence. The repeating variables together must have same number of fundamental dimensions. Next, fifth one, two variables should not have same dimensions. So you cannot take diameter and length. There's a geometric property as two repeating variable. So that is not possible according to point 5. So two repeating variables should not have same dimension or same unit. Then the following variables are commonly considered as repeating variables. First one dv rho, second one dv mu, and third one hg rho, fourth one dn rho, and fifth one lv rho, and sixth one dg rho. So what is first one dv rho? Where geometric property is diameter, and flow property is velocity, fluid property is density. In second case, geometric property is d, diameter, flow property is velocity, and fluid property is viscosity. Third case, h0, flow property, geometric property is height, and g is acceleration, that is the flow property, acceleration due to gravity, rho is density. And fourth one, geometric property as diameter, an, that is rpm, as flow property, rho as fluid property. And fifth one, lv rho, geometric property as length, v as flow property, and rho as fluid property. And sixth one, diameter as geometric property, g as flow property, and rho as density. So depending on the condition, you can go through, you can select any one of the following, or combination of other thing also possible. So this is some examples given below. You can follow this order, or depending on the condition, you can just select repeating variables. So let us first go for the problem. First problem, resisting force R of supersonic plane during a flight can be considered as dependent upon length of the aircraft L, velocity V, air viscosity mu, air density rho, bulk modulus of air K. Express the functional relationship between these variables and resisting force. So resisting force, from the problem itself we can judge resisting force is dependent on what? So remaining parameters, that is velocity, mu, rho, and K. K for bulk modulus. So first step we have to write, categorize into dependent and independent variable. So R is dependent, and length, velocity, mu, that's viscosity, density, and bulk modulus are independent variables. Hence R is a function of LV, mu, rho, and K. Mathematically, R can be expressed as R equal to F of L, V, mu, rho, K. Take it as equation 1. Then I have to simplify that expression. So, or it can be written as F1 of R, L, V, mu, rho, K. So take it as expression 2, that is dimensionally homogeneous expression. Now I have to count the number of variable. Therefore total number of variable that includes both independent as well as dependent. So R, L, V, mu, rho, K. So 6, n equal to 6. Now I have to write the dimensions of various variables. For R, that's a force. So how to get dimension for force? F equal to ma, mass into acceleration. Unit of mass is kg, unit of acceleration is meter second to the power minus 2. So overall dimension for force is meter, kg meter s to the power minus 2. So dimension becomes ml t to the power minus 2. Then velocity, as we all know, distance by time l t to the power minus 1. Then mu, Newton second per meter square. So Newton can be again obtained from F equal to ma. Then you can rearrange and you can get dimension for mu. We get as m L to the power minus 1 T to the power minus 1. Then rho, that is kg per meter cube, mass by volume, so m into L to the power minus 3. Then bulk modulus, very important thing, capital letter K, it has unit same as that of pressure. So what is the unit of pressure? Pressure unit is Newton per meter square. So again Newton can be obtained from F equal to ma divided by meter square. So we can get expression for or dimension for K as m into L into T to the power minus 2. This is a dimension for bulk modulus. So from you can look into these dimensions of various parameters or variables. We can see m, L and T terms in almost all cases. So number of fundamental dimensions, that is m equal to 3. So according to Buckingham Pi theorem, it can be, the problem can be grouped into pi n minus m pi terms. So what is n? N here 6 and m here 3. So 6 minus 3, that becomes 3. So that means we should have 3 pi terms in a problem. So 3 pi terms, say pi 1 comma pi 2 and pi 3 are formed. So we can have 3 pi terms, pi 2 pi 3, pi 1 pi 2 pi 3. So it can be it is obtained from n minus m, that is n is 6, m is 3, 6 minus 3 is 3. So we can tell like we can have 3 pi terms. Next, equation 2 can be written as f1 of pi 1 comma pi 2 comma pi 3, that is equal to 0. That is taken as equation 3. So next let's go for step 2. So each pi term contains m plus 1 variable. So here m is number of fundamental dimension. M, it is already we obtained from parameters as equal to 3. So each pi term should contain 3 plus 1 variable. So what is 3 plus 1 equal to? That is 4. So 4 variable each pi term. So number of repeating variable should be equal to number of fundamental dimension. So out of 4 term, 3 is repeating and one more term is other thing, other variable. So 3 plus 1. So out of the 5 remaining variables, one variable should have geometric property. Okay, each pi term equal to m plus 1 variable, where m is equal to 3 and also called repeating variable. That's what I told. Out of 6 variable r, l, v, mu, rho and k, 3 variables are to be selected as repeating variable. R is a dependent variable and should not be selected as repeating variable. That is according to point number 1 of methods of selecting repeating variable. R cannot be taken as repeating variable because it is a dependent variable. Out of the 5 remaining variable, one variable should have geometric property, the second variable should have flow property and third one should have fluid property. These requirements are fulfilled by selecting L, V, rho as repeating variable. So we can see the problem, there is no diameter term. So we can give importance to now length as geometric property. Then there's a second is a flow property, there is a velocity term. So V as flow property and third one should be correspond to fluid property. So we can see then mu as well as rho. So we can give importance to, always should give importance to density. So it is rho. So L, V, rho are taken as repeating variable. So these repeating variables themselves should not form a dimensionless term. So they should not form dimensionless term. You can see the unit dimension of L is L only and V is L into T to the power minus 1 and rho is m into L to the power minus 3. Upon clubbing together, we are not going to get m to the power 0, L to the power 0, T to the power 0. So that is proper. Next, dimensions of LV rho are L, Lt to the power minus 1 and m, L to the power minus 3. And hence 3 fundamental dimensions exist in LV rho and they themselves do not form dimensionless group. So from looking into the dimensions, we can see we are not going to get m to the power 0, L to the power 0, T to the power 0. So they are not forming dimensionless group. Next, step 3. Each pi term is written as, so we have to write expressions for pi term. From n minus m, we got it as number of pi term equal to 3. So 3 pi terms respectively pi 1, pi 2, pi 3. So pi 1 equal to geometric property L, first one repeating variable correspond to geometric property L. second one flow property that is V, and third one fluid property into some other parameter or variable. So pi 1 equal to L to the power A1 into V to the power B1 into rho to the power C1 into R. Pi 2 equal to L to the power A2 V to the power B2 rho to the power C2 into mu. Pi 3 equal to L to the power A3 V to the power B3 rho to the power C3 into K. Take it as expression 4. Each pi term is solved by principle of dimensional homogeneity. That is, left hand side dimension should be equal to right hand side dimension concept. We can get values of A1, B1, C1, A2, B2, C2, A3, B3, C3, and we can back substitute in expressions for pi 1, pi 2, pi 3, and we can get values of pi 1, pi 2 and pi 3. So first pi term, that is pi 1. For the first pi term we have m0, l0, t0. So pi 1 is the dimensionless, so it has no dimension. So m to the power 0, l to the power 0, t to the power 0. That is equal to L to the power A1. L has dimension L only, small letter L. So dimension is capital letter L. L to the power A1, velocity has dimension L t to the power minus 1. So L t to the power minus 1 into to the power B1 into rho to the power C3. So rho has dimension M L to the power minus 3 into resisting force. It has dimension M L t to the power minus 2. Now, very easy concept, equating the powers of m, l and t on both sides. So power of m, so that is 0 on left hand side, and right hand side it is m to the power c1 and into m. So c1 plus 1, so c1 equal to minus 1. So power of el, equating the power of el, on left hand side it is l to the power 0, right hand side it is l to the power a1, l to the power b1, l to the power minus 3c1 and L. So expression becomes 0 equal to A1 plus B1 minus 3C1 plus 1. Next, we can get expression from that for A as A1 equal to minus B1 plus 3C1 minus 1. So power of T, equating the power of T. So left hand side T to the power 0, right hand side T to the power minus B1 and T to the power minus 2. So expression becomes 0 equal to minus B1 minus 2. So from that we can get expression for B1 as a value of B1 as that is equal to minus 2. So we can back substitute that value in equation 2, like values of C1 and B1 we already got. So we can get value of A1 by substituting in equation 2. So A1 equal to minus B1 plus 3C1 minus 1. So B1 value is minus 2 into minus, that becomes 2, then plus 3C1, C1 value is minus 1, 3 into minus 1, that becomes minus 3, minus 1, that is equal to minus 2. Now substituting the values of A1, B1 and C1 in pi 1. So that is, we get pi 1 equal to L to the power A1, that is A1 value is minus 2, L to the power minus 2, V to the power B1, that is V to the power minus 2, B1 value is minus 2, rho to the power C1, C1 value is minus 1, so rho to the power minus 1 into R. So here you have to make it is rho to the power minus 1, not rho to the power minus 2. So that is equal to, just rearrange, R it has positive power, R to the power 1, so it remains in numerator, divided by rho L square. So that's what I told, rho has power minus 1, so when it goes to denominator it becomes positive, rho divided by L square, or R divided by rho L square V square, L square V square. So that is like L to the power minus 2, V to the power minus 2, rho to the power minus 1, that goes to denominator and becomes positive. So R divided by rho L square V square, there is an expression for pi 1. Take it as expression 5. Similarly, second pi term. For second pi term we have pi 2 equal to L to the power A2, V to the power B2, rho to the power C2 into mu. So substituting dimensions on both sides of pi 2, m to the power 0, L to the power 0, t to the power 0, that is equal to L to the power A2, Lt to the power minus 1 to the power B2 into m L to the power minus 3 to the power C2, m L to the power minus 1 T1, t to the power minus 1. So now equating the powers of m, l and t to get values of A to B to C2. First let's equate power of m. So on left hand side it is 0, right hand side m to the power C2 and m. So 0 equal to C2 plus 1. So C2 value is minus 1. Next, equating the power of L to the power 0 on left hand side, L to the power A2, L to the power B2, L to the power minus 3C2, L to the power minus 1 on right hand side. So we get expression as 0 equal to A2 plus B2 minus 3C2 minus 1. Then equating the power of t, on left hand side it is t to the power 0, right hand side it is t to the power minus b2, t to the power minus 1. So 0 equal to minus b2 minus 1, so b2 value equal to minus 1. Now we have values of b2 and c2, now remaining value is a2, so we can get from second expression. So we can just rearrange second expression as a2 equal to minus b2 plus 3c2 plus 1. So minus b2 value is minus 1. So minus into minus, that becomes plus. So plus 1 plus 3c2. c2 value is minus 1. So it becomes minus 3 plus 1, that is equal to minus 1. Upon simplification we get value of a2 as minus 1. Now we can substitute a2, b2, c2 in pi2 term. So pi2 equal to L to the power minus 1 as a2 value is minus 1, b to the power minus 1 as b2 value is minus 1 into rho to the power minus 1 as c2 value is minus 1 into mu. So that is equal to, upon rearrangement, mu has positive power mu to the power 1. So that stays in numerator, mu divided by L to the power minus 1, v to the power minus 1, rho to the power minus 1, that goes to denominator and becomes rho to the power 1, L to the power 1, v to the power 1. So mu divided by rho LV. Next, third pi term, that is pi 3 equal to L to the power A3, V to the power B3, rho to the power C3 into K. So where K is bulk modulus, it has same unit as that of pressure intensity. Now substituting the dimensions of on both sides of pi 3. So we have to substitute dimensions on both sides, m to the power 0, L to the power 0, t to the power 0, that is equal to L to the power A3 into L t to the power minus 1 to the power B3 into m L to the power minus 3 to the power C3 into m L to the power minus 1 t to the power minus 2. So K has a dimension m L to the power minus 1 t to the power minus 2. Then equating the powers of m, L and t on both sides. So just we have to equate powers of m, L and t on both sides. First let's go for equating the power of m. So by we have m to the power 0 on left hand side, and right hand side we have m to the power c3 and m to the power 1. So expression we get it as 0 equal to c3 plus 1. Therefore c3 equal to minus 1. Then equating the power of L, on left hand side we have L to the power 0, right hand side L to the power a3, L to the power b3, L to the power minus 3c3, L to the power minus 1. So 0 equal to a3 plus b3 minus 3c3 minus 1. Then equating the power of t, we get, on left hand side we have t to the power 0, right hand side t to the power minus b3, t to the power minus 2. So 0 equal to minus b3 minus 2, therefore b3 equal to minus 2. Now we have values of c3 and b3, and we can substitute c3 b3 value in second expression and we can get value for a3. So a3 equal to minus b3 plus 3c3 plus 1. So b3 value is minus 1. So minus into minus 2, that becomes plus 2. Next, plus 3c3. c3 value is minus 1. So 3 into minus 1, that becomes minus 3 plus 1 equal to 0. a3 value we got it as 0. Then substituting these values of a3, b3, c3 in pi 3, we get pi 3 equal to L to the power 0, V to the power minus 2, rho to the power minus 1 into K. So that is equal to, upon rearrangement, K divided by L to the power 0, that is 1. So it has no value. So V square rho. So K divided by rho V square. That is the expression for pi 3. Next, last step, step 5. Substituting the values of pi 1, pi 2, pi 3 in equation second. So that is F1 of pi 1 comma pi 2 comma pi 3, that is equal to 0, that is the equation second. So f1 of r divided by rho L square V square comma mu divided by rho LV comma K divided by V square rho, that is equal to 0. Now we have to get expression for resisting force. So that is first pi term. So I'll express first pi term as a function of remaining pi terms. So r divided by rho L square V square is equal to function of mu divided by rho LV comma K divided by V square rho. So I can cross multiply rho L square V square to the other side. So expression for R becomes as R equal to rho L square V square function of mu divided by rho LV comma K divided by rho V square. There is the expression for resisting force. So that is the first problem. So second problem, the efficiency eta of a fan depends on density rho, dynamic viscosity mu of the fluid, angular velocity omega at a diameter d of the rotor, and the discharge q. Express eta in terms of dimensionless parameters. So this was a question asked in December 2014, January 2015. So here they ask expression for eta. So eta is dependent parameter, so that depends on rho, that's density, viscosity, angular velocity, diameter and discharge. So those are independent parameters. So expression for efficiency can be written as efficiency eta equal to function of rho mu omega d q. So expressing dependent variable as a function of independent variable, or we can rearrange that expression as, or we can rewritten as f1 of eta comma rho comma mu comma omega comma d comma q equal to 0. Take it as expression 1. So as we can count here, eta rho mu omega d q, we have total number of variable equal to including dependent and independent, it is 6, n equal to 6. Now we have to get value of m. For that we have to write dimensions of all the parameters or variables. So eta, as we all know, efficiency, that is output by input, it is unitless. So it has no dimension. If it is not having unit, means it is not it will not have a dimension also. So eta equal to dimensionless. Rho equal to, that is kg per meter cube. So ml to the power minus 3. Mu, as we all know how to get expression for mu, unit is Newton second per meter square. So dimension becomes ml to the power minus 1 t to the power minus 1. Then omega, angular velocity. So angular velocity is radian per second. So radian has no unit, per second. So t to the power minus 1 as a dimension for omega. Then diameter, that is measured in meter. So dimension is L. And discharge, that is volumetric flow rate meter cube per second. So dimension becomes L cube t to the power minus 1. So we can see here m, L and t terms. So m equal to number of fundamental dimension equal to 3. So according to pi theorem, we can get a number of pi term as n minus m, that is 6 minus 3, that is equal to 3. So we have 3 pi values, the pi terms, pi 1, pi 2, pi 3. So equation 1 can be rewritten as f1 of pi 1 comma pi 2 comma pi 3 equal to 0. Take it as expression 2. Next, each pi term contains m plus 1 variable. M is number of fundamental dimension, so that is equal to 3 from problem. So m plus 1, 3 plus 1 variable, so total 4 variable. So out of 4, repeating variable should be equal to number of fundamental dimension, that is m equal to repeating variable, that is equal to 3. Now we have to select the fundamental repeating variables. So how to select? First one should correspond to geometric property, second one flow, third one is density, that is the fluid property. So here first one is, we can see the problem, diameter is a geometric property, there is no length, so we can take diameter as geometric property. Then there is no velocity, instead of that we have angular velocity, so we can consider omega as a flow property, and mu and rho, so you should give importance for rho, that's density, as fluid property. So choosing d omega rho as repeating variable, we have pi 1 equal to d to the power a1 omega to the power b1 into rho to the power c1 into eta. So pi 2 equal to d to the power a2 omega to the power b2 into rho to the power c2 into omega. Pi 3 equal to d to the power a3 omega to the power b3 rho to the power c3 into q. These are the expressions for pi terms, that is pi 1, pi 2, pi 3 in terms of repeating variable and one more variable. So total 4 variable, out of which d omega rho are taken as repeating variable multiplied by some other remaining variable. Next, let's go for getting expression for pi 1, first pi term. Substituting dimensions on both sides of pi 1, m to the power 0, L to the power 0, t to the power 0, as pi has no dimension, so m to the power 0, L to the power 0, t to the power 0, that is equal to L to the power a1, diameter has dimension L, and t to the power minus 1 to the power b1, this angular velocity has dimension t to the power minus 1, into density to the power c1, density has dimension m, L to the power minus 3 to the power c1, m0 l0 t0. So efficiency, as I already told, it is dimensionless, so m0 l0 t0. So now equating the powers of m, l and t on both sides, we get, by equating the power of m, on left hand side m to the power 0, right hand side m to the power c1, m to the power 0. So 0 equal to c1 plus 0, therefore c1 equal to 0. Then equating the power of l, so on left hand side L to the power 0, right hand side L to the power a1, L to the power minus 3c1, L to the power 0. So 0 equal to a1 minus 3c1 plus 0. Next, equating the power of t, on left hand side we have t to the power 0, right hand side t to the power minus b1 and t to the power 0. Therefore b1 equal to 0. So we can substitute back b1 and c1 in value in second expression, and we can again get value of a1 as 0. So substituting the values of a1, b1, c1 in pi 1, we get pi 1 as pi 1 equal to d0, d to the power 0, omega to the power 0, rho to the power 0 into eta. So that is equal to eta only. So when we have the repeating variable multiplied by any dimensionless term, then we are going to get dimensionless term as the pi term. So you can directly write that thing, otherwise you can just go through the procedure like this. Next, second pi term, that is pi 2. Pi 2 equal to d to the power a2, omega to the power b2, rho to the power c2 into omega into mu. So substituting dimensions on both sides of pi 2, that is m to the power 0, L to the power 0, t to the power 0 equal to L to the power a2, t to the power minus 1 to the power b2 into m into L to the power minus 3 to the power c2, m L to the power minus 1, t to the power minus 1. So mu has dimension m L to the power minus 1, t to the power minus 1, just writing dimension on both sides. Then equating the powers of m, L and t on both sides. So first let's go for equating the power of m. So on left hand side we have m to the power 0, right hand side m to the power c2, m to the power 1. So 0 equal to c2 plus 1, so c2 equal to minus 1. So there is a value for c2. Then equating the power of L, L to the power 0 on left hand side, L to the power a2 on right hand side, L to the power minus 3 c2, L to the power minus 1 on right hand side. So 0 equal to a2 minus 3 c2 minus 1. Then equating the power of t, t to the power 0 on left hand side, L to the t to the power minus b2 and t to the power minus 1 on left hand side, sorry, right hand side. So we get expression for t as 0 equal to minus b2 minus 1. So from by equating the power of t, we get expression as 0 equal to minus b2 minus 1, therefore b2 equal to minus 1. Now we have values of b2 and c2 equal to minus 1, so we can back substitute in expression 2, so we get a value of a2. So 0 equal to a2 minus 3c2 minus 1, therefore we can get a2 value as minus 2. So we can now substitute values of a2, b2, c2 in pi 2. There is a pi 2 term. We get pi 2 equal to d to the power minus 2, omega to the power minus 1, rho to the power minus 1 into mu. So as values of a2 is minus 2, b2 is minus 1, c2 equal to minus 1. Now we can rearrange mu to the power 1, that is positive, so that is in numerator, mu divided by d to the power minus 2, omega to the power minus 1, rho to the power minus 1, that goes to denominator and becomes d square omega rho. So mu divided by d square omega rho. This is the expression for pi 2. Next, last one, third pi term, that is pi 3. So pi 3 equal to d to the power a3, omega to the power b3, rho to the power c3 into q. Now substituting the dimensions on both sides of pi 3, we get m0 l0, m to the power 0, L to the power 0, t to the power 0 equal to L to the power a3, t to the power minus 1 to the power b3, m L to the power minus 3 to the power c3, L cube t to the power minus 1. So for q, dimension is L cube t to the power minus 1. Now equating the powers of m, L and t on both sides. So by equating the power of m, we get expression. So on left hand side m to the power 0, right hand side m to the power c3. So 0 equal to c3, therefore c3 equal to 0. Then equating the power of L, we get on left hand side it is L to the power 0, right hand side L to the power a3, L to the power minus 3c3 and L cube. So we get expression 0 equal to a3 minus 3c3 plus 3. Then equating the power of t, we get expression t to the power 0 on left hand side, t to the power minus b3 on right hand side, t to the power minus 1 again on right hand side. So 0 equal to minus b3 minus 1, therefore b3 equal to minus 1. Now we have values of b3 equal to minus 1 and c3 equal to 0. Substitute in expression 2 and get value of a3. So upon substitution we get a3 value as minus 3. Now substituting the values of a3, b3, c3 in pi 3, we get pi 3 equal to d to the power minus 3 omega to the power minus 1 rho to the power 0 into q. So rearrange. So q is numerator, in numerator q divided by rho to the power 0 is 1, so you can neglect d cube rho. So q divided by d cube rho, that is the third dimensionless term or pi term. So now we can substitute values of pi 1, pi 2, pi 3 in equation 2. So that is f of pi 1, pi 2, pi 1, pi 2, pi 3 equal to 0. So what we are going to get? So substituting the values of pi 1, pi 2, pi 3 in equation 2, we get f1 of or f of eta mu divided by d square omega rho q divided by d cube omega, that is equal to 0. So this first pi term is equal to eta and second pi term equal to mu divided by d square omega rho, third pi term equal to q divided by d cube omega. So we can just substitute in expression 2 and get expression for eta as, upon rearrangement we have to express first pi term as a function of remaining pi term. So I'll take pi out and I can express pi as a function of remaining pi term as eta equal to function of mu divided by d square omega rho q divided by d cube omega. So that is the expression for efficiency. So I have to get expression for efficiency like this. Efficiency is dependent parameter, whereas remaining variables are independent parameter. So n minus m pi term. So n is number of variables, pi m is number of fundamental dimension. So in order to write m, you have to look into the dimensions of all the variables. Then each pi term should contain m plus 1 variable. So m equal to repeating variable, a number of fundamental dimension, so into multiplied by one more variable. Then you can solve the expression. We can write expressions for pi 1, pi 2, pi 3, so on, and we can get the expressions for pi 1, pi 2, pi 3 upon substituting values of a1, b1, c1, a2, b2, c2, so on, and we can express one pi term as a function of remaining pi term. So that is the procedure involved in Buckingham Pi theorem. These are the two examples. In next video I'll come up with the remaining problems or 3 to 4 problems. Thank you.